So far during this session, we've had two different talks by Andrew Churchill, who was the one presenting earlier. And the previous talks were kind of focused on different data products, where the data products were still kind of in like a raw form where we just had the data elements and there was no additional analysis on top of that. And so this afternoon, we'll kind of get a little bit deeper into that actual data analysis, and we'll share some of the data and kind of illustrate how we can leverage some of this high fidelity data that the system's generating to answer important questions. And so the topic of the talk right now is going to be the benefits of pre-scheduling into the overhead stream with the EOBTs. So the EOBT stands for the earliest off-block time, and that's a prediction provided by the airlines that says, you know, we think this aircraft will be able to push back, say, at 12 o'clock noon, and then we leverage that prediction, you know, within our own kind of internal models to generate what we would call unimpeded takeoff times, which ultimately end up, you know, being used as input by the scheduler to generate the target takeoff times. And so, so the idea here is that we'll talk a little bit about some of these benefits from pre-scheduling into the overhead stream with the EOBTs, and this is really analytic focused, you know, so for somebody like me who likes the data, it's very exciting. So just to begin with, we'll start off with an overview of what the ATD-2 concept is. And so the main idea here is the ATD-2 is the name of the project. IADS is the name of the tool, the Integrated Arrival Departure Surface. So you can see here that the full IADS concept has, you know, departures, has those arrivals. It also has the surface, potentially multiple airports operating within a Metroplex environment. So, you know, the purpose of today's talk isn't really to rehash what the whole IADS concept was, but what we really want to focus on here is kind of illustrated in with these circles is we want to talk about what we say is APRA, or the approved request for overhead stream insertion. And the key idea here is that, you know, some aircraft need to merge into a congested overhead stream, and so they need to coordinate their takeoff time such that they can seamlessly merge into this overhead stream. So for example, we show an aircraft here. This aircraft took off at this origin airport, and then it flies across, you know, these different, either the terminal airspace and then this center boundary, ultimately to merge into the overhead stream. And the key idea here is that to merge into this overhead stream slot, this departure should take off from its origin airport at what we call the controlled takeoff time. Sometimes I'll call that the CTOT, controlled takeoff time. And then compliance to that controlled takeoff time is an aircraft is said to be compliant if it takes off anywhere between 2 minutes early and 1 minute late. So you have this very small 3-minute window on the surface of the airport to take off to be compliant to merge into this overhead stream. So this is the APRA, and this is kind of the context of, you know, what we'll be talking about in the remaining slides here with compliance and also trying to measure how much delay, you know, TBFM, who is actually scheduling in this overhead stream, is passing back to the surface of the airport. So when that overhead stream gets congested, the idea is to pass that delay from the airspace back to the surface. So to begin with, we can share some of the compliance data that we're seeing at Charlotte. So here, the horizontal axis is time. Essentially, the left-hand side is the start of ATD-2, which started in September 2017. The right-hand side is we have data all the way through July 30th. And then each, you'll see some gray data points here. Those gray dots are the daily compliance for any given day. So each gray dot here represents a day. If, say, 72% of the APRECs were compliant on that given day, we would plot a gray dot at 72. And then now, so each day here is represented by these gray dots. And then you could say, okay, well, can I calculate the moving average of these gray dots? So here, the blue line represents that 2-week moving average, and the orange line represents that 6-week moving average. So what we can see here, and we kind of highlighted down here at the bottom of the slide here, is that what we see when we kind of take this 35,000 foot view of APRA compliance at Charlotte is that there's been a steady increase of APRA compliance over the life of the project. Not only has there been a steady increase, but one of the things, you know, when you think about the future of the NAS, and there's a lot of talk about different things like trajectory-based operations, in order to achieve kind of trajectory-based operations and be efficient, you need some kind of level of predictability. And here, not only are we increasing the compliance, but the predictability of that compliance is increasing as well. How can you tell that? The spread of these gray dots has really tightened up. Look at these last couple months. We only have this small handful of gray dots down here, whereas look at previously. It used to be, right, that essentially the worst day in ATD-2 during calendar year 2019 was equal to the average day at the start of ATD-2. So we've really kind of improved compliance through the life cycle of the project, not only compliance, but the predictability of that compliance, which is very important in trajectory-based operations. So this is just general APRA compliance at Charlotte. And, but the title of this talk is about pre-scheduling with EOBTs. So we've started pre-scheduling at 2 destination airports. So departures that are going to Atlanta Airport, we now pre-schedule with EOBTs. And also departures that are going to Chicago O'Hare Airport, we pre-schedule with the EOBTs. The process here that we talk about is that it used to be that a flight, when the pilot was ready to push back, would call, you know, ATC, and they'd say, I'm ready to push back. ATC says, okay, well, you're APREC'd. You need to request a time. They then, once the pilot's ready, request that time, potentially are, you know, delayed at the gate or on the surface to meet that overhead stream. But with pre-scheduling, the idea is 20 minutes prior to when we think that pilot is actually ready to push back, the system automatically triggers a request to TBFM and says, I want to schedule this aircraft in the overhead stream, assuming that it's going to push back in 20 minutes. So then the surface system kind of leverages its predictive models and the automation to request that, that controlled takeoff time. And so, as I said, the 2 destinations that we started pre-scheduling, the first one is in Atlanta, and we started, I think, roughly around October of 2018. But again, this is just the 35,000 foot view of APRA compliance into Atlanta Airport. And we see the same kind of general trend that we see this in compliance increasing throughout the life cycle of the project. And also that predictability is increasing. You can see here the gray dots are really tightening up. You can see kind of a little bit of leveling off here. A lot of that is due, you know, in the summer months during the stormy season, things get very complex. And so we're right in the heart of the stormy season the last couple months. And so it's actually quite amazing that, you know, controllers are still able to achieve this type of compliance. For those that can't see, because I understand the graphics aren't great, this tick mark here is 70% compliance. This tick mark here is 80% compliance. So we're achieving nearly 80% compliance for our APRECs into Atlanta, which is really kind of remarkable when you think about the complexities of the Charlotte surface. So as I said here, This is the second destination into OHare. We've only been pre-scheduling into OHare for about a month, so we don't really have a lot of data yet to kind of look at the pre-scheduling into OHare. We have a little bit we'll show towards the end of the slides, but again, this is our 35,000 foot view of just APRA compliance from Charlotte into OHare. And again, I think, we can see the same thing, which is this trend upwards, the predictability improving. One thing to keep in mind, whereas at the airport level, we might have a lot of APRECs, say like 70, 80 per day. At this destination of OHare, we might only have a handful of APRECs. So if you only have 5 APRECs and you miss one of them, you're already down to 80% compliance. Question? Sorry. So this is kind of that 35,000 foot view of OHare. And so really, I think, if you were to ask me, what am I learning from these graphs? I would say, well, we're learning a little bit that we're improving compliance and things are becoming much more predictable, but, there's still kind of a lot left desired of, how is the system performing? What kind of benefits are we seeing and that kind of thing. And so we have some other views of APRA compliance as well that give us a little bit better insight into exactly what's going on. And so here's one of the additional views we have of APRA compliance. So again, the horizontal axis here is now cumulative number of APRA flights. And then what you're seeing here is this rolling average of the last 10,000 APREC flights. So if we just continuously look back and say, tell me what my compliance was on my last 10,000 APRECs, and then every day I step forward and say, tell me what the compliance was on my last 10,000, and continue this process, we can create a graph like this. And what you can see here is that since the life cycle of ATD-2, we have scheduled roughly 42,000 APREC flights, and that this is a rolling window of the last 10,000 sampled at every 100. And what I think this view really gives insight into is this inflection point. And so what you see here is that compliance improved a little, and then we kind of hit this leveling out period, but then now you can see there's an inflection point and compliance seems to just kind of been turbocharged all of a sudden. And what happened here at this inflection point is when we began to introduce a lot of the phase 2 capabilities into the IAD system. What do I mean by the phase 2 capabilities? We kind of outline it here, that once we started integrating the electronic flight strips, once we got Atlanta Center using IDAC, once we started pre-scheduling with the EOBTs, and then finally we also had some scheduler improvements that we implemented along with the phase 2 work. So we kind of had all these factors come together, and unfortunately, being that it's a field demonstration, we weren't able to kind of roll out each one of these new components individually in some isolated environment to say, okay, well, what's the impact of my AEFS integration? And then test the system for 3 months and then say, okay, what's the impact of just having Atlanta Center using IDAC? Things become messy during field demonstrations. So we kind of had to roll all of these out together. Sometimes Al jokingly likes to say we had to throw the kitchen sink at this one to really see some improvements. So to us, we can't really say, well, we think 10% is coming from this and 20% is coming from this. Overall, we just say that together somehow kind of these new capabilities has really generated this uptick here in compliance. And so overall, I think our feeling is that we find this this trend here kind of very encouraging, and that we just, we think a lot of those phase 2 capabilities are providing real benefits that are being seen in the NAS here. So again, this is kind of this kind of aggregated view to say, okay, well, let me kind of look backwards at the last 10,000 APRECs and see what my compliance looks like. Well, you could say, well, that's great, but that's at the airport level. I'm a flight, I'm taking off runway 36 center. What's different for my life versus this other aircraft that's taking off on runway 36R or vice versa in a different flow? So we're able to actually take these kind of compliance and split them up by runway to start to kind of understand, is there any kind of trends or relationships here where one flow gives us better compliance or one runway gives us better compliance? And so we kind of did this. And because now once we break the data up, we can't kind of aggregate over our last 10,000 as easily because there's not as many APRECs. Here is aggregated from the last 3,000 cumulative APRECs. But for those that know Charlotte, this probably won't be much of a surprise. What we found when we did this is that one of our runways seemed to be kind of operating at higher compliance than the other runways. And I apologize if you can't read the legend here, but this is runway 36 center. The other runways here, down here 36R is in red, 18L is in orange, 18C is in blue. And so, for those that know Charlotte and the operations, this kind of makes sense. North flow is definitely our, for lack of a better word, least complicated flow. Things get a little bit more complicated in the south. And then the center runway is a departure only dedicated runway, whereas the east runway, 36R, accommodates both departures and arrivals. So when you have that dual use runway, it kind of makes life a little bit more difficult when you have a 3-minute compliance window that you have to take off in, and now every 2 minutes comes in an arrival. So I think this result was something that we were expecting. What kind of got us to scratch our head a little is we thought that the center runway in south flow would kind of look similar to the center runway in north flow, but that what we see in the data is that the north flow tends to be a little bit simpler than the south flow. And intuitively, I think if you talk to any of the controllers there at Charlotte, they would tell you, well, duh, like things are complicated in south flow. So that was how we kind of broke things up about the runway. So that kind of is just a very high view of compliance. And if I were to say, well, the take-home message that we see in the data is that compliance has steadily been increasing during the life cycle of ATD-2. Not only has compliance been increasing, the predictability has been increasing, and that when we look back and we try to understand what capabilities led to this increased compliance, our feeling is those phase 2 capabilities. And again, we can't isolate any one, but we have this set of phase 2 capabilities that we think together really kind of bumped the needle into the positive direction there. So moving forward, so far we talked about compliance. Compliance is one piece of the puzzle here that we're trying to understand. But when you think about pre-scheduling with EOBTs, the idea here is that as I schedule earlier, instead of waiting for the pilot to be ready, I schedule 20 minutes prior to when the pilot's ready to push back. The idea there is that 20 minutes gives you a little bit less congestion in the overhead stream. Once the overhead stream is less congested and I'm trying to schedule into that overhead stream, then you can just shave off a little bit of that delay that's being passed back from the overhead stream to the surface of the airport. So that's kind of the main idea here. And so for these next slides, we're going to talk about the impacts of the delay being assigned to these APREC flights. But before we can talk about the impacts of the delay, we just have to get on the same page here and define a couple metrics that we're going to measure. So imagine here this is kind of time, and now the life cycle or the flight will have these different discrete events. And so imagine here this black dot. I apologize for the bad formatted text, but imagine here that this black dot is the scheduled off block time. So this is when kind of, the scheduled off-block time is, but the pilot might be ready earlier or later than the scheduled off-block time. We never really know. Then if the pilot is ready, say here at the pilot ready time, and we leverage our internal model under the hood that tells us about the unimpeded taxi time, you can take the pilot ready time plus the unimpeded taxi time, and you get what we call here the unimpeded takeoff time at pilot ready. So again, it's benchmarking the unimpeded taxi time to the pilot ready time, and that's essentially saying, we think that if you're ready here and nobody else is on the surface, you could take off right here. But there are other aircraft on the surface. There is congestion on the surface. And so we generate a prediction that we call the earliest feasible takeoff time, and that prediction essentially is accounting for this congestion on the surface. So if there's 7 flights in front of me that need to take off, then my earliest feasible takeoff time should reflect the fact that I'm going to be in a 7 aircraft queue, and so on. Ultimately, this earliest feasible takeoff time prediction is passed to TBFM, and TBFM uses that as an input to generate what we call here, which is the controlled takeoff time. The controlled takeoff time is that ultimate time that aircraft should comply to merge into the overhead stream. So again, if we just kind of outline these different data elements and metrics we're going to measure here, we have the pilot ready time. Pilot ready time plus unimpeded transit gives us the unimpeded takeoff time. The difference between the earliest feasible takeoff time and the unimpeded takeoff time is essentially the surface congestion, and we call this the surface excess taxi time. It's essentially the predicted queue. And then ultimately, TBFM is going to come back with some additional delay, and the difference between the earliest feasible takeoff time and the controlled takeoff time is what we will call the TBFM assigned delay. So for those that want to play along, maybe write this down, take a picture, burn it into your retinas or whatever, because we'll talk about some of these metrics here. So, and one other thing too is that when we look back here, this requires our high fidelity IAD system data. What do I mean by this? We talked in the earlier sessions, nobody else has pilot ready time except for ATD-2. So if you were to look in the TBFM data, if you were to look in even the future TFDM data, you won't have pilot ready time. So, these are some of the metrics for the APRA times, but then we want to say, well, if we try to validate or verify some of the findings or trends we see in our high fidelity data, how can we do this? This is another metric that actually is within TBFM that we can leverage. So this metric is the scheduled off-block time. So again, that's just kind of the scheduled published time that this aircraft kind of books its tickets with. And then the earliest feasible takeoff time, as I mentioned, is something that is provided to TBFM as an input. So this is actually a metric that we can measure external to the IAD system to try to validate the findings we see in our high fidelity data. And you'll see how we do that there in a second. So now that we kind of understand the different times, what do these different metrics look like before and after pre-scheduling? So the first one that we look at, if we come back to here and you were to ask me, what do I think is the most fair time to look at? I think that where we got is that we said, well, the most fair time to look at is the controlled takeoff time minus the unimpeded takeoff time. Why is this the most fair? Because if the pilot's ready, and this is how long it takes to taxi to the runway, then this difference between when they show up at the runway and when their control time is, to that flight, they don't care if that delay is coming from the surface congestion, if it's coming from TBFM. It's essentially, some type of delay that aircraft is going to incur, whether it be the surface excess taxi time or the TBFM assigned delay. So for the first metric that we look at, we're going to look at, again, the controlled takeoff time minus the unimpeded takeoff time at pilot ready. And this combines both that surface excess taxi time and the TBFM assigned delay. So this is a, for lack of a better word and, to use a dirty word, this is the total delay that that aircraft is experiencing. So here it is. And so on the horizontal axis is, again, this is the start of ATD-2, October 2017. This is the full month of July here at the very end. I have a vertical red line here to say pre-scheduling started in October 2018. One thing that I would keep in mind here is that when we talked about the phase 2 capabilities, one of the phase 2 capabilities we mentioned was scheduler updates. Those scheduler updates came in December 13th, so about 2 months after we pre-scheduled. And our feeling is that during this time, from October 2018 until essentially the beginning of December, we were going through a calibration exercise. And that it wasn't, able for us to just take this system out of the box, plug it into Charlotte, and have it work perfectly out of the box. So we had a little bit of period of calibration, and we think that if you want to kind of judge the system, that the most fair way to do it is to judge it starting in December once kind of that system was calibrated and we included those new scheduler updates. So that's why we have these data points here circled. So what am I showing here is, again, the controlled takeoff time minus the unimpeded takeoff time. So it's the total delay. And the blue line here is the median. The orange line here is the mean. And this middle one here is the standard deviation, or another kind of, that tells us about the predictability. We want lower standard deviation, gives us more predictable total delay. And then in the bottom here, this really helps us kind of visualize the distribution, where the dark purple represents the 50th percentile of delay. The middle purple represents the 75th percentile or quantile of delay, and the very, very light represents the 90th. And so what I think you can see here is that if you're interested in this controlled takeoff time minus unimpeded takeoff time, that there have been significant improvements here on that predictability of that delay once kind of we started pre-scheduling with the EOBTs and after the calibration of the system. So I think that this is something that we really kind of are seeing and saying, wow, we're seeing some real benefits here from the surface, from the pre-scheduling with the EOBTs using the surface system. And that overall, that we see improvement not only in kind of that standard deviation and predictability, but also in the mean, and I'll show that here in a second. So if I were just to take all my data after December, and I'd take all my data to the left of this red line, and I say, okay, let me take all this data to the left and call this the non-pre-scheduled flights. Then let me take all this data basically that's circled here since December to the right and call that my pre-scheduled flights. And I take this metric, controlled takeoff time minus unimpeded takeoff time, and I just put it into a histogram. Here is what you see, where the orange is the pre-scheduled flights and the blue is the normal APRA flights. And I should mention this is into Atlanta Airport because that's where we're doing the pre-scheduling, where we have the most data. And what you can see here is that where you have this darker orange color, that's where the two histograms are overlapping. So you have both the blue and the orange on top of each other. What you see here is that these flights here have a higher chance of kind of this reduced delay after pre-scheduling, and that before pre-scheduling, these flights have a heavier right tail. So again, keep in mind the metric we're looking at, controlled takeoff time minus unimpeded takeoff time, compare before and after. And what we see here is that before pre-scheduling, we essentially had an average, for lack of a better word, total delay of 8 minutes with a standard deviation of 20.6 minutes. After pre-scheduling, that delay dropped from 8 minutes down to 7.4 minutes. So about a 0.6 minute reduction in the average, but we had a 4.3 minute improvement in the standard deviation, that predictability of that delay. And so we find that very encouraging. And you know, that not only are we improving the mean, but we're really improving that standard deviation there. So we kind of saw these results and we said, okay, this is great, great stuff here. We really are encouraged. Can we kind of correlate what we see here in our high fidelity data to some of these other systems, like I'm saying the TBFM system, which might not have kind of that same high fidelity data, and can we recover benefits like what we're seeing in our data? So we said, okay, let me look at the controlled takeoff time minus the earliest feasible takeoff time. So what data element is this? If we go back to our little cheat sheet here, the controlled takeoff time minus the earliest feasible takeoff time is essentially that TBFM assigned delay component of the total delay. And so this really should tell you about the overhead stream. This is the difference between the time you give to TBFM. You say, I can take off at this time, the earliest feasible takeoff time, and then TBFM comes back with the control time. So this is purely TBFM assigned delay. So again, what did we see? We saw in the surface system, when we use our metric that we think is fair, that we saw a reduction in delay of 0.6 minutes and over a 4-minute improvement in standard deviation. So we said, okay, let me focus purely on that TBFM assigned delay component, see if I can recover similar results. And this is, so we actually have a guy who goes in and he taps into the TBFM systems and parses all the binary files and everything like that, and we can extract data directly from TBFM. That's where this data is coming from. And again, pre-scheduling started in October. The system was really calibrated in December, and then after December is where we think, you know, is probably the fair comparison. And so we look at this and we say, wow, like, I looked at our high fidelity metrics and I saw these great improvements. And then I look at this metric, which is that controlled takeoff time minus earliest feasible takeoff time, that TBFM assigned delay component. And you might have to squint pretty hard at this to find kind of similar types of benefits here. And so this really kind of confused us. And we said, you know, well, let me look at the histogram just to double check that like I'm not going crazy here or anything like that. So again, this is that TBFM assigned delay component. And what do we see here as well? We do see a slight reduction in the amount of delay that TBFM is passing back to us from 4 minutes down to 3.7 minutes, but the standard deviations are almost the same. And so again, we scratch our head and we say, I'm not really sure how this makes sense. Like, you know, we have a system. The only thing we're doing is we're trying to schedule a little bit earlier so that TBFM might be a little bit nicer to us and they can kind of assign us a little bit less delay. And overall, I'm seeing all these improvements, but then when I go back to the metric that kind of these improvements were supposed to manifest from, I'm not able to recover that same level of benefit. So like, what's going on here? And so we said, okay, well, this is interesting. Like, let's really kind of dig into this. And so what I'll show you next, I would just, you know, preface in the fact that, you know, this is still research. We're collecting the data, we're trying to understand, but our feeling is, you know, we're all friends here, so we can kind of share what we see in the data and kind of share it with the community. And so we said, okay, well, let's go back and think about again, what are our metrics? So again, what we found was that if we took the controlled takeoff time minus the unimpeded takeoff time, we saw a lot of benefits in this total delay metric. However, when we focused purely on that TBFM assigned delay, we didn't see the same types of benefits. So we said, okay, what else can we look at? Well, this is where this metric comes in. The idea here is that, you know, from the flight's perspective, the controlled takeoff time is really a function of two things. One thing being the earliest feasible takeoff time, and one thing being the controlled takeoff time, how much delay TBFM is bringing back. What do I mean by this is that, let's say I'm an aircraft and I'm ready to push back at 12 o'clock noon. If, not that the controllers would do this, but just as a thought experiment, if the controller says my earliest feasible takeoff time is 4 p.m., even though I'm ready at 12 o'clock noon, and then TBFM comes back with 0 delay on top of that, you're not really having 0 delay from that flight's perspective. You have to wait until that earliest feasible takeoff time that was provided to TBFM, because your controlled takeoff time can't be any earlier than this. So what do I mean by this is that if the predictability of the earliest feasible takeoff time is improving, the predictability of the controlled takeoff time will improve. If this final component, the TBFM assigned delay, is essentially the same before and after pre-scheduling, however, after pre-scheduling, the times that we are providing to TBFM are becoming much, much more predictable, then overall, if this is much, much more predictable, and the difference here, the TBFM assigned delay, is essentially unchanged, then overall that controlled takeoff time is much, much more predictable. So what do I mean by this is, so let's focus in on this earliest feasible takeoff time minus the SOBT. So this is essentially the time that is provided to TBFM. Before pre-scheduling, it was done by the human controllers. After pre-scheduling, this EFTT is being generated by the surface system, by the automation. So what do we see here? Again, this top graph is the blue is the mean, and the orange is the median. The middle graph here is that standard deviation, i.e. that kind of predictability. The lower the standard deviation, the more predictable. And again, here is kind of that visualization of that distribution. And so what I think you're seeing here is those improvements in the predictability of my total delay are not being driven potentially by the fact that the TBFM assigned delay component is coming back much, much more predictable. What it's being driven by is the fact that the original times that are being requested and sent to TBFM potentially are becoming much, much more predictable. So if I have a little bit of delay kind of padded on top of a much, much more predictable time, overall my controlled takeoff time is much more predictable. And so how can we look at this again in the histogram view? So again, the orange is after pre-scheduling. So this is essentially that earliest feasible takeoff time benchmarked against the scheduled off-block time. And the orange is those pre-scheduled flights where the surface automation is requesting the time. And the blue is before pre-scheduling, where essentially the human TMC is requesting the time. And what you see here is that the surface system is requesting slightly earlier times than the human TMC was requesting, but then also that standard deviation is improving by 2.2 minutes. And you could say, oh, okay, well, you know, in your high fidelity metrics, we saw a 4-minute improvement in the standard deviation. How come, you know, we're only seeing essentially a 2-minute improvement here in the standard deviation? And I would say that kind of that final component is dealt with in the fact that if you look at this, that really we're benchmarking this metric off of an SOBT, whereas that high fidelity total delay metric is being benchmarked against kind of the unimpeded takeoff time, which is back to the pilot ready time. And so I think that this little bit of kind of error here between when the pilot's actual ready and the scheduled off block time is where those last couple minutes of predictability are really coming from. So again, this piece of the work is still research. I think, you know, we're trying to understand this. So, you know, what I'm saying here is kind of where we think the data is leading us to, but I wouldn't kind of exactly write it in pen in the gospel just yet. So I think we're at the point where we just want to keep collecting this data to try to understand, how the system's working and what type of benefits we're receiving. So the last thing here is I showed you all this data for Atlanta, and I started the talk saying, okay, well, we're also pre-scheduling into OHare. So what does the data look like for OHare? This, again, is our metric that we think is the most kind of fair, that controlled takeoff time minus the unimpeded takeoff time, so the total delay, the TBFM, and the surface excess taxi time. And we only have 1 month of data here for OHare, but I think overall our feelings is that OHare is starting to show some of the same benefits that we were seeing in the Atlanta data. And so we just want to continue to collect the OHare data and try to confirm that what we're, all those same benefits we saw for Atlanta, we also can recover here for OHare. Last thing that we'll get into here, and this kind of relates to one of the questions that was asked in the earlier sessions, is, as I said, we had to calibrate our system, and it took some time to calibrate. And so I would say the next couple slides are some of the ways that we look at calibrating the system. So, and by calibration, the time that we provide to TBFM, the earliest feasible takeoff time, has a buffer in it, and that buffer could be adjustable for flights with EOBTs versus flights without EOBTs. How aggressive or conservative do we want to be with those kind of requested times? So those are the kind of questions we try to answer here with these next graphs. So what do we see here is we see 3 data sets. The blue are essentially just general APRECs out of Charlotte. The orange are APRECs out of Charlotte to Atlanta, but that were in that pre-scheduled data set. And the green are APRECs out of Charlotte into Atlanta that are in that pre-scheduled data set. And so what we show here is this is the percentage of flights that do not reschedule. This is the percentage of flights that reschedule their controlled takeoff time for a later time. And this is the percentage of flights that reschedule their controlled takeoff time for an earlier time. And I apologize, that you can't see the numbers, but we can download these slides. What we see here is that essentially roughly 74% of flights do not reschedule before pre-scheduling. So these are normal APREC flights. About 74% do not reschedule. However, you can see the green here, which is our pre-scheduled data set, drops down to about 63%. So once pre-scheduling happened, we had a little bit less flights that kind of maintain their original controlled takeoff time. However, what I think we're most interested in is, what percentage of those flights are essentially rescheduling for later times, and did introducing pre-scheduling increase or decrease or kind of maintain that percentage of flights that have to reschedule for a later controlled takeoff time. And what we see here is that after pre-scheduling, this is our percentages that reschedule for later times, that we're essentially the same. We go from 18.7% to 19.6%. So less than 1 percentage difference of the number of aircraft that reschedule for later times. So we find that very encouraging. But you could ask, okay, well, where did all these flights here that used to keep their old schedules, where did they go? They're here rescheduling for earlier times. One other thing to keep in mind here is that the percentage that are rescheduling for later times and earlier times during pre-scheduling are pretty similar, about 19.6 to 16.6. So only about a 3 percentage point difference. That's one of the ways that we think about. So we have a multitude of metrics that we can think about when we think about the buffers to the system and how we calibrate the system. This is one of them. You know, I don't want 30% to reschedule for later times and 5% to reschedule for earlier times, or vice versa. It's nice to keep it even. It's telling you that, you know, you're kind of being fair somewhat. So I think that we found this encouraging, that we went through this process. We're seeing some benefits to compliance that we started with. We're seeing some benefits to that kind of total delay that these aircraft are being assigned. And then moreover, the same number of aircraft are essentially rescheduling for later times. So that's very encouraging. One last way we can look at this, and then this is kind of my last 1 or 2 slides, and then we'll open it up for questions, is that we can say, okay, well, when we talk about rescheduling, is there a relationship between the EOBT compliance and if an aircraft rescheduled for an earlier or later time? So on here, the horizontal axis is EOBT compliance, where the negative represents a flight that called ready earlier than EOBT, and the positive represents a flight that called ready later than EOBT. So if 12 o'clock noon is your EOBT, and you're the pilot and you call at 11:55 and say I'm ready to push back, you would get a -5 value. If you call at 12:05, 5 minutes late, and say I'm ready to push back, you would show up here. And then here we kind of show a stacked histogram where, again, the blue are the aircraft that are not rescheduling. The orange are aircraft that are rescheduling for earlier times, and the green are aircraft rescheduling for later times. Here I'm showing the CDF of those histograms. So the cumulative distribution function is just another way to kind of visualize these distributions. And then down here, what this tells us is that if you go to a given value, say 0, so at perfect EOBT, this tells you the percentage of flights that call later than whatever you're at on the horizontal axis. This graph tells you the mixture. So for example, you know, if you ask a question, for all flights that call kind of later than this -5, what's the mixture? You would say, okay, well, 70%, you know, do not reschedule, and 20% reschedule for later times, and 5% reschedule for earlier times. And what you can see here in this histogram is that this is our data before pre-scheduling, and that what this histogram is telling us is that there is no relationship between the EOBT compliance and the rescheduling prior to pre-scheduling. And that kind of makes sense, because if you think of the process, it doesn't matter if you're late or earlier or whatever with EOBT. The old process was when you were ready, you called the ATC and requested a control time. Once you got that control time, you start moving towards the runway. And so again, whether you were late, early, whatever with EOBT, the fact that you wait until you're ready to request that control time, there's no relationship between EOBT compliance and whether I'm rescheduling for earlier or later times. However, once we started pre-scheduling, we found a relationship between EOBT compliance. How can we see this? Is if you look at this CDF, there's a gap. If you look at these CDFs, they're on top of each other. Those distributions are the same. Once we started pre-scheduling, what do we see here is that there's a lot more orange aircraft that reschedule for earlier times when they are early, and almost no orange when they're late. If you're late with respect to EOBT and you were pre-scheduled based on your EOBT, it's very hard to reschedule for an earlier time. Moreover, you can see it here in these kind of CDFs. For example, you know, the percentage of aircraft that reschedule for a later time, this green, only 40% have called ready by EOBT. Whereas compare that to aircraft that reschedule for earlier times, nearly 100% have called ready at or before EOBT. So now we're recovering this relationship that we expect, which is that aircraft that call earlier with respect to EOBT have a higher chance of rescheduling for earlier times. Aircraft that call late with respect to EOBT have a higher chance of rescheduling for later times. And then this final graph, again, if you kind of compare it here, there's almost no change. Any value on this horizontal axis kind of is the same. Whereas afterwards, you see there's this cross. This cross tells us that essentially, if you look at all aircraft that call later than EOBT, roughly 50% of them do not reschedule, where roughly 50% of them reschedule for later times. So again, that bottom graph is telling us about that mixture of aircraft who call later than the given value. And so, for example, if you were to say, okay, aircraft that call more than 5 minutes late with respect to EOBT, almost 80% of them are rescheduling for later times, which makes sense. You are assigned a time based on your EOBT, you show up 5 minutes late, you have to reschedule for a later time. I can't make that time. So I believe that that is my last slide. So I can pull up the conference IO here to, yes?
Does the current ATD-2 display pre-scheduled times on flights? Because I only see the APRA release times. I don't remember seeing pre-scheduled times on the
Yeah, so the question was, does the ATD-2 display show the pre-scheduled time? So those APRA times will come through, and that is the pre-scheduled time. The main difference is that instead of waiting until the pilot's ready and the pilot calls ATC, we do that 20 minutes prior to when we think the pilot is ready. So they might still be boarding that flight. You know, the ramp controller could look out the window, you know, the jet bridge is still attached. They have 10 more minutes of boarding. However, we're triggering that kind of schedule.
So without them calling you anyway?
Yes. Yes.
That's also displayed on the ramp display, so they see it as well.
Once that control time flows through, yes, it will be distributed to ramp and ATC. Yep.
The last slide that you showed over here, those numbers, are they numbers on flights in picking up the back or driving back?
This is indifferent. I should mention, and I didn't mention, but thank you for reminding me, is that, yeah, the question was, the flights that are in this graph, are they kind of at the beginning of the bank, the end of the bank, or anywhere across the bank? So these are flights that are anywhere across the bank. However, and thank you very much for asking this question, because I forgot to mention that these flights have been filtered down to flights that receive 0 delay from TBFM, because we're really interested in understanding the relationship between EOBT and rescheduling. And so our feeling is that if you receive a lot of delay from TBFM, you could be quite late with your EOBT and still kind of be on time. So this is a filtered down view of only those flights that receive 0 TBFM delay, and it's trying to tell us, are we being too aggressive or too conservative with the earliest feasible takeoff times that we're requesting? So this is one where essentially the controlled takeoff time is equal to that earliest feasible takeoff time that we provided to TBFM. Yes?
Did you notice any improvements in actual taxi out times?
Yes, so for the question was, did we notice any improvements for actual taxi out time? So perfect. Yeah, so the next talk will be benefits of the surface system. And for these controlled flights, we like to hold them on the gate if they receive any kind of real delay. And so that's one of our benefit mechanisms, is these controlled flights that schedule their control times while still at the gate. We have the ability to gate hold them if they kind of have to be delayed. Yes?
First, I'm glad you clarified the assumptions you made to take the 0, the flights that are
Yeah.
as if they're not going to be late, because your data shows almost a perfect normal car.
Mm-hmm.
And we know in real practice, in the real world, in the actual world, that's a bit
What's,
Say DFW, because we're looking at ATL. What can that mean to DFW? And the reason why I'm saying that is because you might improve by 0.6 minutes, right? But you only looked at 5 flights. But if you improve by 0.6 minutes and you look at 1,000 flights, then it becomes significant. And then now you have to say the significant level of that for reasonable, for it to look reasonable. And basically what I'm saying is your validation or interpretation of the results. It is really important because it helps me say from DFW to make a decision. And then the last thing I might say is when the standard deviation moves from by 3 minutes or 4 minutes, what does that mean to variance? Which is a very important factor to consider when you're looking at an immediate time, because you want your variance to be as small as possible for you to accept the results.
mhm. Yeah, so one thing I would say is that we're not necessarily improving the unimpeded times, but we're benchmarking against the unimpeded times. And so when we calculate excess taxi time or delay or something like that, it's benchmarked against those unimpeded times, which we get from the historical kind of just percentages and things like that.
And actually, one last point. So when I like the way you define, the times and how you are getting more time and the differences. But when you put up the slides, kindly give us the definition of each variable, let's say pilot training, because the way I would interpret it, maybe it's not the same way somebody else would interpret it. It helps us to have a universal language, and it's one of the issues we're having in the aviation world right now. And I'm just using terminologies like accepted delay, unaccepted delay, delay time. So you find what it means to the airport is different from what it means to the airlines. It's different from what it means to FAA, other entities. So just to help us understand, please define those values for us so that when we adopt your system, we know what exactly we're doing. Thank you.
Yep. Yeah, I think that's a good point. And we always try to maintain consistency with the TFDM terminology, but even within the FAA themselves, they're not consistent. You talk to a TBFM person and they would call the earliest feasible takeoff time the ready time. You talk to a TFDM person, they call it the earliest feasible takeoff time, what's the ready time? So I kind of sympathize with your feelings there. So we have to move along to the next presentation, but if anybody has any additional kind of, let me make sure, do we have a break in between or no? Okay. Okay, yep, so please enjoy your 10 minutes and then we'll share some of the benefits of surface metering after the break.